Example problem 1 is a Poissier's law problem. So Poissier's law says that the higher the viscosity of a fluid is, the more pressure or the more force it's going to take to make a fluid move. So think about pouring out a bottle of water as opposed to pouring out a bottle of syrup. You have to squeeze that syrup bottle a little bit harder than you have to squeeze the water bottle to make the water come out as opposed to the syrup, because syrup has a higher viscosity than what water does. So it takes more pressure. You have to push that bottle in harder to get the syrup to come out of the container instead of just pouring out a bottle of water. So that's what Poissier's law is, and that's what this next equation is all about. So Poissier's equation, as you saw from the previous slide, is volume flow rate, so we're seeing that variable again, equals delta P, so that's that difference in pressure that we talked about, times pi, radius to the fourth, divided by the number 8, this little n, and so this is going to be the variable viscosity, and then L is going to be the length. And so, of course, the volume flow rate is measured in cubic meters per second, as always. Pressure is Pascal. Pi is just a number, so it's not measured in anything. Radius is always meters. Length is always meters. Viscosity, as you can see here, is measured in units of pascals per second. And 8 is just a number. It has no unit of measurement. So let's see if we can't figure out what the problem is asking us for. So the problem says a drug is being delivered into a patient's arm at a rate of 10.0 milliliters per minute. So we have a volume flow rate right here. So volume flow rate equals 10 milliliters per 1 minute. So we already know that volume flow rate is not in its correct units. So let's just keep reading the problem. The drug is being delivered into a syringe through a 5 centimeter long needle. So that's going to be your length, 5.0 centimeters, which we also know at this point is not in the correct units, with a diameter of 1 millimeter. So our diameter is 1 millimeter. Once again, the diameter, which is ultimately going to convert to the radius, needs to be measured in units of meters. So it is not in its correct units either. If the patient's blood pressure is 110.0 millimeters of mercury, what must the pressure in the syringe be? So it's asking us for delta P. This information right here is useless. It doesn't mean anything in terms of the actual calculation itself. So literally everything that we have here is in its incorrect units. So we have to put all of this stuff in the correct units. So let's start with volume flow rate. So 10 milliliters per minute. We need to be in units of cubic meters per second. We have some conversion factors right here. But we need to be in units of liters first, not milliliters. So we're going to go ahead and convert from milliliters to liters. That way we can use our conversion factor here between liters and cubic meters. And so we give the 1 to the thing with the prefix and the metric system constant to the base unit. And then we use our conversion factor that's provided to us. So in 1 liter, there is 0.001 cubic meters. So now we've handled the cubic meters. We need to go ahead and handle the time. So minutes goes on top and seconds goes on bottom. In 1 minute, there is 60 seconds. And so this has already been done in a previous problem. And if you want to go back and rewatch exactly how and why this conversion is done, it's in a previous video and it goes a little bit slower than where I'm going in this video. So milliliters cancels, liters cancels, we're left in cubic meters. Minutes cancel, we're left in seconds. So we're good to go with the units. Now let's put this into our calculator. So 10 times 1 times 10 to the minus third times 0.001 divided by 60 equals 1.667. So 1.667, or you can just keep it at 1.67 if you'd like to. times 10 to the minus 7 cubic meters per second. So that's going to be our final volume flow rate. So we're good to go there. Length was our next one that we needed to turn into meters. So we have 5.0 centimeters. We're going to meters. We're going from something with a prefix to a base unit. So that is going to be a one-step conversion. So giving the 1 to the thing with the prefix and the metric system constant to the base unit. And so centimeters cancels, we're left with meters. So 5 times 1 times 10 to the minus 2 is 0.05 meters. And that is, again, going to equal our length. So I'm going to begin circling these. That way we can identify them later. Not have to look too hard on the page. The next thing that we have is our diameter that equals 1 millimeter. We have a formula here for how to find the radius, because if you look up here at the Poissier's law equation, we need a radius, not a diameter. So we have to divide by 2. And so 1 divided by 2 is going to be 0.5 millimeters, because that's what it says here. We need to be in units of meters, not millimeters. So times, millimeters goes to the bottom, meters goes on top, because we're going from something with a prefix straight to a base unit. Nothing else with a prefix. It's a one step. So give the 1 to the thing with the prefix, metric system constant, 1 times 10 to the minus 3 to the base unit. And so you can see where milli cancels. So 0.5 times 1 second e to the minus 3, that equals 5.0 times 10 to the minus 4 meters. And that is going to equal our radius. So we've got our volume flow rate, we've got our length, we've got our diameter. We know what pi is. We already know what the viscosity, our little n, is. And so it looks like we're ready to go. We're ready to rearrange this equation. So we're going to continue the equation on this page over here. So again, that formula was volume flow rate equals delta P times pi r to the 4 divided by 8 in L. And we're looking for delta P here. So there's going to be quite a bit of rearranging to get delta P by itself. So first of all, we want to move this 8 in L. So we're going to multiply by 8 in L and treat it all as one variable. Since there's a denominator here, we want to move 8 in L out of the denominator. So what we do to one side, we have to do to the other. So times 8 in L. After you do that, the equation looks like 8 in L volume flow rate equals delta P pi R4. And again, we want to isolate that delta P. So at this point, you just divide by pi R4 to get it to cancel. Divide by pi R4. And so our final equation that we're going to be working with is delta P equals 8 in L F divided by pi R4. And so we can plug in everything that we know at this point because we've calculated everything. We might have to go back a page though. So 8, if we go back to look at the volume flow rate from the problem, it was 8.90 times 10 to the minus 4. So 8.90 times 10 to the minus 4 pascals per second. Length, we calculated to be 0.05 meters. So 0.05 meters. Volume flow rate, we calculated to be 1.67 times 10 to the minus 7. So 1.67 times 10 to the minus 7 cubic meters per second. And so that is our numerator divided by 3.14 because that is the value for pi. Now r, before we put it into the equation, we have to do r to the 4th. And so going back to look at our radius, it was 5.0 times 10 to the minus 4. So 5.0 times 10 to the minus 4 to the 4. And so let's put that in our calculator just like that. 5.0 times 10 to the minus 4 to the 4 equals 6.25 times 10 to the minus 14. And so we can go ahead and put that 6.25 times 10 to the minus 14. And this is radius, so we're here in meters. So now we're ready to get just a numerator and just a denominator. So delta P equals. So in your calculator, 8 times 8.90 second E to the minus 4, 0.05, and 1.67 second E to the minus 7. That equals 1.945, or 5.9452, sorry. 5.9452 times 10 to the minus 11 divided by 3.14 times 6.25 second E to the minus 14, and that equals 1.9625. So 1.9625 times 10 to the minus 13. And that looks a lot more simpler than this does up here. So in your calculator, 5.9452 second E to the minus 11 divided by 1.9625 second E to the minus 13 equals 302.94. And we're calculating delta P, so it's pascals, and that is going to be our change in pressure for this viscous fluid. Let me know if you have any questions about example problem 1.